determination in the Mathcad of forces acting in finite elements in a local coordinate system. This is article number 4.15 of the book Mechanical Systems Calculations of the Marine Facilities. So we consider the exercise of finding the forces in the statically indefinable mechanical system, that is the statically indefinable frame, with the degree of static indefinability 5. Originally, in the article 4.10, we began the exercise, and first we set the initial data of the geometry. So we had to use the method of finite elements in the Mathcad computer algebra system. So to do the finite element decision, we have to specify we have to set the initial data in the vector form. So we did the initial data of the geometry in the article 4.10. In the article 4.11, we set the data and did a little bit transform of the data of the external forces section. So we considered the data of the concentrated forces applied to the nodes, and besides we reduced in the article 4.11, second lesson, for definite one exercise, we the concentrated distributed load acting on the finite elements number 2, number 3 of the assigned statically indefinable frame. We reduce it to the nodes, to the nodal application. So in the next article 4.12, we worked with the development of the we worked out the stiffness matrices of finite element in the global coordinate system associated with the statically indefinable frame. And in the next, we did the stiffness matrix in the article 4.13, stiffness matrix of the discrete model of the statically indefinable frame. The discrete model is the vector description of the concept of the combining of the separate finite element into unit one mechanical system. That is the discrete model. We do that by the use of the methods of vector geometry and algebra, and this we did in the article 4.13. In article 4.14, we determined the displacements of nodes by the product of the stiffness matrix, inverse stiffness matrix of the discrete model of the statically indefinable frame. We product this by the vector of the nodal load got in the second lesson in the article 4.11. And besides, in the article 4.14, we did we worked out the matrices and the matrices of the stiffness of finite elements separate in the local coordinate system, local system associated not with the integral mechanical system, but associated with the with each finite element. And after that, we have nowadays in this definite one lesson. This is article 4.15. We have to find the displacements of the nodes. From the displacements of the nodes, we have to determine having the displacements of nodes got in the previous one lesson 4.14. We have to find the end displacement of the separate finite elements in our considered mechanical system. After that, we have to transform the displacements of the finite element to the local systems, local coordinate systems. After that, we have to determine the forces acting in the elements of the mechanical system, vectors of the forces in the elements of the mechanical system, using the the matrices of stiffness of finite elements in local coordinate system, but in the previous exercise 4.14 article, using the matrix, auxiliary matrix of cosines, of transforming of the vectors from the global to local coordinate system, using the matrix of the displacements of nodes in the global coordinate system, in displacement of the ends of the finite elements and got in the global coordinate system. This we transform to local coordinate system, and using the nodal loads of the under the action of the distributed forces, the nodal loads, but we got this in the second lesson in the article 4.11 for the we got the nodal loads under the action of distributed forces. We got this in the global coordinate system associated with the discrete model, and now we have to define this nodal loads found. We have to define the nodal loads in the local coordinate system of each finite element. So this is a sixth lesson of the exercise of finding forces acting on finite elements in a local coordinate system, and article number 4.15 of the book Mechanical Systems Calculations of the Marine Facilities. Okay, first of all, a little bit about the transformation of the local coordinate system to the global coordinate system, and the global coordinate system to the local coordinate system. So the vector, any vector, could be the vector of the any force r. We can see here on the figure 4.15.1. In the global coordinate system has the coordinates as global coordinate system. We say ix from the point I, the reference point I, x, y, abscissa axis x and y, and the vector r has a coordinates r1 and r2, r1 and r2. In the local coordinate system with the same reference point I, but local coordinate system inclined to the global coordinate system to the angle alpha. The same vector has coordinates, the projections, the components of vector in the coordinate system, in the inclined coordinate system, r1 stroke and r2 stroke. The stroke mean that this is a coordinates of vector r in the local coordinate system. We consider the local, the inclined coordinate system to the definite angle alpha to the global coordinate system, and the global is with horizontal abscissa axis x and the vertical ordinata axis y. The n characteristic converting of finite elements specified in the global coordinate system into the corresponding characteristics in the local system, which is termed in the global coordinate system by angle alpha for the initial and for the end. So we have the coordinates for the initial I and for the end j of the rod. So we rotate the rod in the global coordinate system. We rotate the system of the coordinates from the global one to the local one to the angle alpha in the system of coordinate, in the original one system and in the local one system rotating, which turned by the angle alpha relative to the global coordinate system. We have the rod. The rod characterized by the first end and the second. At the first end, or the beginning of the rod, has the coordinates r stroke I. This is a vector r stroke I. And the end has the coordinates r stroke j. So the vectors are of the beginning of the rod r stroke 1, r stroke 2, etc. I, and the end is r4 stroke r5 stroke r6 stroke with coordinate j. And when we have the coordinate in the global coordinate system, we can by the product of the cosine matrix, cosine of the angle of inclination, cosine alpha, sine alpha minus sin alpha, cosine alpha, the angle of inclination of the local coordinate system in the global coordinate system by the product of this matrix, matrix product by the vector of the coordinates in the local coordinate system. This is for the beginning of the rod in the coordinate system. We can find the coordinates of the same vector beginning in the local coordinate system. The same we can do for the end of the considered rod. So having the coordinates of the end of abscissa, ordinata of the end of the rod, and the angle of the bending. That's coordinate for the rod system. We have the first one is abscissa, next one ordinata, and the third is the bending. The bending is angular displacement, angular coordinate of the rotation of the end. So we can transform by the same cosine matrix to the R4 stroke, R5 stroke, R6 stroke. This is the coordinates of the end of the rod in the local coordinate system, which is inclined to the angle alpha relative the global coordinate system. So by the product of the cosine matrix, cosine always say the auxiliary matrix, the product of this matrix by the coordinates of the end of rod element, rod finite element in the global coordinate system, we can find the coordinates in the local coordinate system. In the matrix form, in the matrix form, more compact form, we can say collapsed form. The more compact form, we can indicate that the coordinates of a vector in the local coordinate system of the beginning of the vector equal to the product of the matrix of transform, the auxiliary matrix or matrix of cosine, by the coordinates of the beginning of vector with no stroke. The coordinates with no stroke is coordinates in the local coordinates in the global coordinate system, and with the stroke in the local coordinate system. And this is just only for end and for beginning of the rod element and for the end of the rod element considered as separate points. But if you consider the total rod with 6 coordinates, 3 coordinates of the beginning, abscissa, ordinata, and the angle of the rotation, and the angle of the bending of the beginning. And this is like for the moments, could be the forces applied to the beginning, to the end, and the bending moment into the beginning, and the forces applied to the end, the horizontal force, as in the global coordinate system, the vertical force component and the bending moment. To transform to local coordinate system, we can use the this matrix. This looks like a quasi-diagonal matrix. So we have 2 segments of the same other zeros. Why this matrix is bigger than 2 matrices considered on the previous one slide? This matrix, the final auxiliary matrix, cosine and sine matrix, is bigger than the previous 2 matrices because this 6 element in each row and then 6 element in each column matrix 6 by 6 applied for the rod, for the total rod, not for the beginning, not for the end, but for the total rod simultaneously. And we can set this matrix into the Mathcad page. This matrix looks like T depend on I is T is a function matrix. I is a number of the finite element in the considered mechanical system. We have 4 finite elements. The first finite element is the left one stand from the node 1 to node 2. The second is a horizontal beam rigidly connected in the node 2 for the first one element and hingely connected to other 2 elements in the node 3. This is second element, and the third is the element inclined between the node 3 and node 4, embedded node 4. And the fourth element is a vertical stand between the hinge in the node 3 to the fixed hinge support in the node 5. So this is variable. The number of the finite element is variable here in the function matrix. This auxiliary matrix we consider as a function dependent on the number of the elements, because each cosine, sine, etc. element in the matrix of the cosines and sines auxiliary matrix for transformation from global to local coordinate system depend on the angle of the inclination. Angle of the inclination is data assigned for each finite element. So this is a function on the number of the finite element in the Mathcad computer algebra system. And forces and displacement of rod finite element, and forces are equal to sum of reactions from the other finite elements and from the external load. So we have the forces, and forces to each of two ends of the rod finite element have to be the total. And we consider this as by the formula. We have to define the external forces, which is reduced to the end of finite element. So we have distributed force, but we have to reduce this to the end of the finite element. We did that in the article 4.11 in the second lesson of this definite one exercise. But we did in the global coordinate system. Now we have to do this in the local coordinate system. The stroke of vector is that is in the local coordinate system. And delta is a vector of the displacements, vector of displacements of the ends of finite elements. This is a matrix, matrix T matrix, auxiliary matrix of transformation, because we have the displacement of the nodes forced from the displacements of nodes, which are in the global coordinate system. We first will have the displacements of the ends of finite elements as well in global coordinate system, and this is displacements of the elements in the global coordinate system. But to use the stiffness matrix did in the local coordinate system, we have to transform this vector of the end displacement of finite elements by the transformation cosine and sine matrix to the local coordinate system. So this formula is just disclosure of this one formula of the reactions from the other finite element. This is product of three matrices in this definite one consequence, and this is the external load focused and distributed. The focused external load concentrated to the nodes, but the load acting within the each finite element. The end forces S stroke E for each end of the rod finite element have three components: the projections of local axis, two linear projections, and one angular projection. And the total number of the end force components for each rod finite element on the plane is 6. So if you consider the flat state of the on the plane of the flat statically definable frame, so each finite element, that is each rod, is of two ends, and each end characterized, each end of the each rod characterized by three projections of the external forces, or internal forces, external forces, three projections of end forces. The one projection coincides with the abscissa axis, parallel in the to the abscissa axis. Another one component in the local coordinate system is in the ordinate axis. Ordinate axis perpendicular to abscissa axis, but in the local coordinate system we indicate by the stroke. The abscissa axis coincides with the axis of the finite element, so the beginning of the abscissa axis coincides with the reference point of the abscissa axis coincides with the beginning of finite element, and the axis of the abscissa passes through the other end of finite element from the reference point. And the second is the force in the finite element applied to the end of the finite element, but applied in the direction of the ordinate axis, to component of the end force applied to the beginning of the finite element. The ordinate axis is perpendicular to the abscissa axis, obviously, and began from the reference point, but the place of the intersection of abscissa and ordinate axis is not so much important. Is much more important for the finite element method, the directions, the perpendicular directions, and the association of direction of abscissa axis with the axis of the finite element. And the S3 stroke is the thought effort acts on the beginning of the finite element, that is a bending moment. The same, the element of the longitudinal force, transverse force, and the bending moment applied to the end of finite element. So the force 3 applied to the beginning of finite element. This is S stroke, like a vector with the index I. I mean that for the beginning of finite element is this definite one formula. This is S1, S2, S3 strokes. And the S stroke J is S4, S5, S6 strokes. the efforts applied to the end of the finite element, road finite element. And the vector of the end displacement of finite element in the local coordinate system is t product by the vector of the displacement of finite element in the global coordinate system. This is in the local one stroke. This is the matrix of the transform from the global coordinate system to the local one. This is the matrix. This matrix we did as a function defined in the Mathcad computer algebra system page. And yeah, and this is the product of matrices here in the formula of the definition of the forces acting to the ends of the finite element. Like in these two, in this disclosure of the vector components, of 6 vector components of 2 ends, each 3 forces or 3 efforts, 2 forces in the moment applied to each end of the finite element for the flat frame. So what the difference between the global and local coordinate system a little bit before the use of the matrices? Let me please remind. The global coordinate system has of 2 axes, abscissa and ordinata, and this coordinate system global associates with the total mechanical system, total statically definable frame, and we have the components of the efforts applied to the end, to the beginning, to the end of each road finite element. One component in the global coordinate system parallel to abscissa axis, another one parallel to ordinate axis. The bending moment, actually the bending moment in the global coordinate system and in the local coordinate system associated with this definite one finite element. This the bending moment delta lowercase letter 3 stroke and the delta lowercase 3. These are both same elements, and the factor of the transforming from the global coordinate system to local one, the factor is equal to 1. So as well for the end of the coordinate of the finite element, road finite element in the global coordinate system, we have 2 component of force parallel to abscissa axis and ordinate axis, and the axis, let me remind, coincides with the axis associated with the general, the integral mechanical system, or with the discrete model, and the axis abscissa of the local coordinate system in the global is x and y, but the local associated with definite finite element, reference point usually the beginning of finite element, the axis passes through the second point of the connection to next finite element. This is the axis of the finite element, coincides with the abscissa axis. So we have the longitudinal force instead of the horizontal force here. We can say that instead of the horizontal force, perhaps not the horizontal force, but as a combination of the forces acting to the ends of the finite elements. One is longitudinal force, like the force applied to the beginning of finite element with a stroke delta 1. Delta 4, the same longitudinal force, but applied to the end of the finite element, delta 4 stroke. The transverse force perpendicular to the axis of finite element, that is perpendicular to the abscissa axis associated with the finite element, that is abscissa axis in the local coordinate system. And this perpendicular component of the force is the transverse force, and as well bending moment. That is the difference of the direction of the components of efforts acting in the global on the figure 4.15.3a and in the local 4.15.3b coordinate system, local coordinate system B. So, and let me remind what the directions of the displacement in the discrete model we defined previously. The horizontal direction delta uppercase letter 1, vertical direction delta uppercase letter 2. This is for the movable nodes 2 and 3, and the bending of the node 2, this rigid corner between the first and the second finite elements. The bending is delta uppercase 3, so delta 1, delta 2, delta 3. And for the next is next movable node of the statically definable frame, that is the node number 3. This is a hinge of the connection of 3 finite elements, 3 road finite elements, element number 2, number 3, and number 4. And the displacement of this node is the horizontal one in the global coordinate system due to the direction of the abscissa axis x, delta uppercase 4, and the delta 5, the vertical component of the force of the displacement at the node 3. So other nodes 1, 5, and 4 are embedded in the support, so we do not experience the displacement just only the node 5, but it is not corresponds with any forces. Maybe for the longitudinal forces, node 4, excuse me, finite element number 4 between the nodes 3 and 5 is like hinged by both ends. The finite element of the force type, like a finite element when we consider the truss. This not finite element, the truss, the connection, the hinged connection of all rod elements in the truss. So, first of all, to find the displacement delta stroke of the ends of the finite element in local coordinate system, we have to define the displacement in the global coordinate system of the ends of the rod finite elements of the mechanical system. To do that, we remember the directions of the displacement in the global coordinate system, the directions of the nodes of a discrete model of the considered statically indefinable frame. And we can define the displacements of the what is the displacements of the beginning. In the global coordinate system, the abscissa translational displacement of the beginning of the each of 4 finite elements: a first finite element, second finite element, fourth, and the fifth finite element. So, considering the discrete model, we can see that the displacement of the first finite element, the horizontal displacement of the beginning of the first, it's embedded connection of the first finite element to the support. So the horizontal displacement equal to 0. What is horizontal displacement of the node 2? Is delta 1. Delta 1 is equivalent to delta 1. So delta 1 is for the node, for the second finite element, the beginning is node 2. So the displacement horizontal delta 1. So what is horizontal displacement of the third and fourth finite elements? Third and fourth finite elements. This is fourth finite element and the third finite element. This is a beginning of the node, which is the connection, hinged connection of this two finite elements beginning. So the horizontal displacement equal to delta 4, because the second is the vertical displacement. So yeah, the delta 4, the horizontal displacement, delta 5 is horizontal vertical displacement of the beginning of the third and fourth finite element. Delta 5 vertical displacement of the beginning. This is two finite elements, 3 and 4 directed from the node 3 to node 4 is element number 3, from node 3 to node 5, element number 4. To begin is node 3. This node experiences displacement delta 4 and delta 5. And the displacement coincides with the displacement of the beginning of these two finite elements, 3 and 4. So we have delta 5. All other displacement of the nodes 3 and 4, the inclined element, this inclined number 3 element and the vertical stand number 4, this displacement of the ends is equal to 0, because maybe only we can consider the angular displacement of the node 5, but we do not input it in the number of the unknown variables for definite one, for this considered statically indefinable frame. So we have 5 times statically indefinable frame, and this embedding not allow the horizontal and vertical displacement of the node 5, just only the rotation, but not. But this is the force type finite element, like the element of the truss. So this not experiences the bending moments. It's only the longitudinal force can possible. So the displacement horizontal and vertical of the ends of the finite element number 3 and number 4 is equal to 0, 0, 0. The end displacement of the angular displacement of the beginning of the finite element 5, the angular displacement is 0 as angular of the end of the finite elements. This could be the angular displacement of the node 5, but it is out of our interest due to this element do not experience a transverse load and do not experience the distributed moment, etc. So this finite element experience only the longitudinal stretching or compression. So we consider now the vertical displacement of the beginning. This is the angular displacement of the beginning. This is horizontal displacement of the end, vertical displacement of the end, and the angular displacement of the end of each finite element. So come again. The vertical displacement of the beginning. For the first finite element, vertical displacement is 0 for the beginning. For the second element, beginning, not 2 for the second element. From the minor number to the bigger number, the direction of the finite element. Vertical displacement equal to delta 2 as vertical displacement. So we can just set in the delta 2 is the vertical displacement, and the 5, delta 5, we have vertical displacement of the beginning of the third and fourth finite element. Delta 2 is vertical displacement of the beginning of the second finite element. So the angular displacement for the first finite element 0, angular displacement here we have angular displacement delta 3 for the second finite element, and for the beginning angular displacement. And for the inclined finite element number 3 and the vertical stand number 4 finite element, the angular displacement we do not consider as these elements are hingely connected, and the hinge do not transmit the bending moment. So it's out of our interest for when finding the forces acting on the finite elements. As well, we can consider the ends of the finite elements. The end of the first finite element is the rigid corner 2. So the horizontal displacement is 1, vertical displacement delta 2, and the angular displacement of the end of the first finite element delta 3. So what we have for the first finite element, horizontal displacement delta 1, vertical displacement delta 2, and the angular displacement delta 3. All other angular displacement of all finite elements are ends are out of our interest due to the third and fifth, the third finite element, third inclined finite element is embedded and do not experience the angular displacement, and the fourth finite element hinged, and perhaps there is no the distributed load and the bending moment in the hinge connection of fourth finite element. And these three components for the end of the finite elements for the first, second, third, and fourth, first, second, third, and fourth finite elements, the displacement of the ends. And when defining the correspondence between the displacements of the translational delta 1, delta 2, delta 4, delta 5, or the beginning of the end finite element, and the angular displacement for the beginning delta 3 and delta 4 for 4 finite elements in each vector, we can define this as the dependencies on the number of the finite element as the vector here transposed delta 1 I with the variable I. This is we consider in the next like the function vector dependent on I is the number of the finite element, and in the Mathcad we define this like delta vector function on the number of the vector I, because the each finite element is the variable, the discrete variable for definition of the vector of the displacements of the 1, 2 translational displacement in the global coordinate system, horizontal and vertical of the beginning, and the angular displacement, and 2 translational displacement along horizontal and vertical in the global coordinate system of the end, and the angular displacement of the end. And these components all depended on the number of the finite element in the considered discrete model. So this is a vector we consider in the next as a displacements of displacements function dependent on the number of the finite element displacement vector, the assigned shift column, the sign of the assignment, the transposed description, not the column like here columns, but here we have the row, just computer nevertheless, and the Mathcad computer algebra system considers the delta on I, the function vector of the displacements in the global coordinate system of the ends of the finite element as well as a column. But we just perform as a row because we use a transpose function. So, okay. Next, we'll consider the determination of the concentrated load for the finite elements and the ejection of the distributed load. We did that in the article 4.11 when determining the concentrated loads in the global coordinate system. What is the difference? This is the determination of the concentrated loads and the action of the distributed load. Distributed load, we have the vertical distributed load applied to the horizontal component of the rod finite element, and the horizontal distributed load applied to the vertical component of the rod finite element. Vertical component is the projection of the rod finite element onto ordinate axis, and the horizontal component of projection of the finite element on the abscissa axis. The finite element inclined by the angle alpha to the positive direction of the global coordinate system. And the question we decided in the article 4.11 how to determine the forces acting efforts, not only forces, two components of forces, parallel abscissa axis and parallel coordinate axis, and the thought is the moment, not the force, but the moment efforts. Efforts applied to the beginning and to the end of the rod finite element instead of the application of distributed force as in the method of the finite element. We have to consider the external load only applied to the nodes. So we have to find the equivalent nodal forces equivalent for the distributed load. That is what we did in the article 4.10, the second 4.11, sorry, in the second lesson of the considered exercise. We did that to find the external load in the global coordinate system and the displacements, these displacements, which we had delta 1, delta 2, delta 3, 4, 5, etc. Delta 3, 4, 5, we have 5 displacements in the global coordinate system. To do that, we determined the forces acting on the ends of the finite elements in the global coordinate system. But now, to find the forces acting in the global coordinates in the finite elements, in the rod finite elements, we have to determine the forces acting on the finite element under the general action of the distributed load. But in the local coordinate system, we have to find the forces in the finite element, the end forces. So then forces are longitudinal forces P1 stroke, P4 stroke, two ends. This is longitudinal forces acting on the finite element along the local abscissa axis, abscissa associated with the finite element with the reference point I. And the transverse force we have to define as well. Here we consider the vertical force P2, P5. Now we have P2 stroke, P5 stroke. This is not a vertical force, but this is perpendicular to the finite element and to the abscissa of local coordinate system. Forces in the local coordinate system. This is transverse forces or sharing forces. So we have longitudinal force, we have sharing force. And we had the bending moment applied to the beginning of the bending moment to the end of the rod finite element. The same bending moment we have here, we indicate like P5 stroke, P3 stroke, yes. But actually, this is not the stroke. The magnitudes are the same as P5 and P3 this. So this is the same magnitude. So the inclining of the local system and the global, inside of the global coordinate system, do not impact on the bending moment, only on the projection of the forces on the coordinate axis. If coordinate axis associated with the finite element axis, so we have the longitudinal forces, transverse forces, instead of the horizontal force and the vertical force in the global coordinate system. That was the difference. What we have to do now in the article 4.15 rather than in the article 4.11 when we did in the global coordinate system. Now in local coordinate system, we will consider the what is the end forces if we know the distributed forces. As same as in the article 4.11 for the second lesson in the considered exercise. We to determine the end loads instead of the distributed load, the best way is to consider the beforehand decisions for statically definable single span finite elements, statically definable finite elements, Roth finite elements of single span. This is this we can find in the textbooks, in the directories, and in the internet databases. They got decisions available to use within the finite elements of the transforming of distributed load to the load acting to at the nodes of the finite element. So this is one of the features of the finite element method, that we can distribute the static indefinability of the mechanical system assigned to determine the forces acting on the elements of the system. We distribute the static indefinability to the static indefinability of, instead of the total mechanical system, integral mechanical system, to static indefinability of the separate finite elements of this mechanical system, combined together by the opportunities of the vector geometry and the algebra within the method of finite elements. So for the element of the first type, the finite element first type, we have the first type, the element number 1, embedded by both ends in the to the supports or to the rest part of the mechanical system. We have the formulas indicated here. The first, this is a vector of the 6 components. The first component is how to determine the independence on the angle of the inclination, the horizontal force, distributed force, the vertical component of the Roth finite element, the cosine of the incline of the inclination of the Roth finite element, or the positive direction of the abscissa axis in the global coordinate system. This is the vertical component of the distributed force. This is horizontal size of the finite element, and this is the sign of the angle of the inclination of the finite element to the abscissa axis global coordinate system. This all, this all we have here: qy, qx, lx, ly, and and if it is the first type of finite element embedded by 2 ends to the other part of mechanical system or to the support, how to find this force instead of the distributed load? Yes, equivalent to the action of the distributed load. The formula having the beforehand decision for single span statically indefinable frame is in the system of equation. For P1 stroke, we have P stroke, but this is P1 because the first element of the vector P stroke for the first type of the finite element. The same others. Each element of each of 6 elements, we have 6 elements: P1 stroke, P2 stroke, P3 stroke, the moment, P4 stroke, longitudinal force, P5 stroke is a transverse force, and the bending moment P6 strokes applied to the end. So all these 6 we have here as a formulas independence on the horizontal component of the distributed load, on the vertical size of the finite element, Roth finite element, on the cosine of the inclination, the vertical component distributed load, the horizontal size of finite element, and the sine of the inclination of the element to the positive direction of this axis. So this is standard formulas for the case, for the standard case of single span statically indefinable finite element of the first type, Roth finite element of the first type embedded by 2 ends. So for the finite element of the second type embedded at the beginning and hingely supported or hingely connected to other finite element in the mechanical system by the second end. The formula will be not the same, but a little bit look like, dependent on the elements 1, 2, 3, 4, 5, 6. 6 is 0 because we have the hinge at the end of the finite element, and hinge do not transmits the bending moment. So the distributed force Qx and Qy, the horizontal component of distributed force, vertical component of distributed force, we can reduce to 1, 2, 3, 4, 4, 4 the components of the forces. Longitudinal force at the beginning, longitudinal force at the end of finite element, the transverse force at the beginning, transverse force at the end, and the bending moment, which corresponds to the action, which is the mechanical equivalent to the action of the distributed force. But these all elements of the end force applied to the end, to the ends for the first three, to the beginning of the finite element 1, 2, 3, and the next three 1, 2, 3, and the hinge 0 moment to the end of the second type finite element embedded at the beginning and the hingely connected at the end. So third type of the finite element, the same, they have the standard decision, the formulas to how to find the equivalent node reactions applied to the end of the finite element if we have the distributed load assigned to the finite element. We have distributed load assigned to the horizontal bar between the node 2 and the node 3 of the statically indefinable mechanical system which is under our consideration. And we have the distributed load of two components, the vertical component, the horizontal component applied to the finite element number 3 between the node 3 and the node 4 in the considered statically indefinable mechanical system. So having these components, Qy is the vertical component of the distributed load, Qx horizontal component, this is vertical size of finite element, horizontal size, cosine, and cosine, sine of angles of the inclination, the factors from the standard definition of the end reaction and action of distributed load. So we have all that. Having the considering the available in the directories, in the textbooks, or in the internet decisions for single span statically indefinable finite elements, Roth finite elements. Thus, we distribute the static indefinability of the system by the geometric vector combining of the finite elements, and we distribute the static indefinability to the indefinability of finite elements. And the finite elements indefinability is pre-decided, and we have before had the decisions for statically indefinable elements of any type, first, second, third, and the fourth type. We have the forces, 6 elements of the forces, the longitudinal force, this element, this transverse force, these 2 elements, and the bending moment for the fourth type Roth finite element, which connected by the hinges at each ends of the finite element. So the hinges do not transmit the bending moment, so we have 0, 0 of the moment acting in the finite element of the fourth type under the by the cause of the distributed load Qx and Qy. This force do not cause the appearance of the bending moment at the ends, as we have the hinges at the ends. Only the finite element itself is to be bended, but the bending moments at the ends have to be 0. So next, to set this all the vectors of end forces in the local coordinate system of finite element of the force types, we first have to select and vectorize. Vectorization is the operation available in the Mathcad, which means that there are A assigned, shift column, the sign of the columns and the equality, shift column on the keyboard. And that we assign to the A, and next we have the mathematical equation in the Mathcad vector algebra system, computer algebra system. and we assign that this function is vector that is depends on the I, depend on the variable. So in the next, we do not predefine as the interval of the variation of the index of the A, but this assignment means that we that this magnitude is the vector. This the same magnitude as the vector, and this is a common part of the formulas. So in each of the formulas for the end load under the action of the distributed load for finite element of all types, for the first type, we just allocated the parts of the formulas, which is the common for all the formulas, to make the description in the Mathcad more compact. This is the parts, the common parts of all of the formulas in the vectors of the forces and forces at the finite element independence on the type of finite element, and the common parts we allocated in the predefined before the definition of the vectors of the and forces in the local coordinate system we indicated like the stroke. Yes, and we located these common parts for compact representation of n force vectors for 4 types of root finite elements in local coordinate system. And this definition of the A, B, and D magnitudes as vector assumes that we consider them as the function vectors dependent on the I is a finite element number. Finite element number I is, let me remind, for the finite element of the first type between the nodes 1 and node 2, the vertical stand left 1. Second type is the finite element, the first one embedded by both ends, the second time embedded by the left end, and hinged connected by the second end. And we indicate the I equal to 2, and the type of the second element is second. Third type of finite element is the root finite element is one hingely supported at the beginning and embedded by the end. And in our considered exercise, the number of the finite element is 3. And the fourth type finite element hingely connected by both ends. And in our considered exercise, the number of finite element is 4. So next, after the allocation of the common parts of the formulas in the formulas of the elements of the end forces arising in the if end forces appeared in the at the ends of finite elements, 6 components for each finite element, 3 for the beginning and 3 for the end, independence on the type finite element when we allocate the common parts of the formulas and specify these common parts in the internet as in the Mathcad computer algebra system as vectors. We can compactly define the end forces vectors as the first vector for the first type dependent on the data numbered by the I is the number of the finite element. And in our definite one case, the first finite element is appropriate to the first type, but it could be other. So for the finite element of second type, by the formula for the second type, by these formulas, we did the specification into the Mathcad computer algebra system, like this definite one line is A, B, etc. as here, A, B, D, etc. Is D, here we have, is the common allocated part of the formulas predefined before the definition of the end forces in the local coordinate system with a stroke of the finite elements in the considered statically definable frame. P of the third type in the local coordinate system depended on the number of finite elements. This is the description of the for the third type finite element of these formulas available by the use of the beforehand decision for the standard single span statically definable single rod element, single span rod finite elements, and this is for the force. for the force. And this is just the check, do we define the end force is correct. This is zeros, y zeros, because we do not have the distributed load applied to the first finite element. So we have all zeros, independence of the first type finite element. We have distributed load on the second finite element. And the distributed load we can substitute by the nodal, by the end forces, the vertical force minus 50 and vertical at the node at the first end, at the beginning of the second finite element. This corresponds to the node 2 vertical force minus 15 instead of the distributed load. And this is minus 30 because we have the distributed force applied downward to the second finite element. This as well we can consider for the third. We have the inclined finite element of the length of the 5 meter. So we have this one, the hitch connection to other finite elements we have here. So the moment bending, the third and force is equal to 0. This is the support embedding equal to 42. The moment. This is the force finite element, vertical stand, all zeros. Why all zeros? Because the force finite element do not experience the transverse load, distributed loads. Only the elements of the number 2, number 3 experience the transverse load. So we have the end forces equivalent to distributed load in the local coordinate system, which in each definite one case, the coordinate system associates with the definite finite element, and the abscissa axis of the local system of coordinates coincides with the axis of the each definite one finite element. So next we generalize vectors of end forces in local coordinate system of rod finite elements into a common array. In the Mathcad, the function can be used if the fragment of the page is on the figure 4.15.9. So we did not once use this formula of the combining of the separate vectors or separate matrices into unit 1. This is independence on the type. T is a type. T and I is a number of element. T is a type. So we now consider it exercise, predefined the type as a vector characteristics. So we had a vector of types, and we have 4 types: the first, second, fourth, third, and fourth types of elements, predefined as a vector before the first use of this vector in the formulas of the combining of the matrices of vectors into unit 1, like this formula. So, as for example, we have here the number 4, the 4 numbers of elements. So, in accordance with the definition of vector of type, the fourth finite element in the alpha definite case, the fourth finite element is of the fourth type. It's only in our case. Perhaps in other cases, not perhaps, but obviously in any other cases, the correspondence between the number of the finite element and between the type finite element can be another. Maybe there will be the not 4 finite elements, but maybe 10 other numbers of finite elements, but we have only 4 numbers of the types of finite element. But if we have the finite element of number 4, in our case, this is the vertical stand hingely connected by both ends. This is a vertical stand between the nodes number 3 and number 5. And for this, we have type 4. So if the inner brackets, if the parameters of the if operation type more than 1, yes, we have number 4, so more than 1, so that's true. So the end forces we define as P2, no P1. Oh, is this true? Yes, P2. But if more than 2 in the more general brackets, more, because we have number 4 finite elements with more than 2, so we have to take the P3 and then the most general brackets. This is consequence of the operations of the if. Each second operation if is within the parameters of the previous one. And if more than 3, so we have the end forces due to the definition of the vector P4. And so we generalize all these vectors P4, P3, P2, and P1 strokes in the local coordinate system as they're understood by the Mathcad computer algebra system, one array in the Mathcad. We indicate this array like this definition, shift columns, two buttons together on the keyboard. This is Py array in the Mathcad of the vectors of the node forces under the action of distributed load. Okay, so the total n forces in local coordinate system in the finite elements of the given statically definable flat frame are determined in the Mathcad fragment of the page indicated here on the diagram 4.15.10. So this is a formula. The forces in the finite elements of number y. This is a vector function, dependent on the I is the number of finite element, equal to ky is the stiffness matrix of finite element, the local coordinate system with the stroke we predefined before today. On this definite one lesson, dependent on I, on the number of finite element, because the type of element depends on I. That's why we have the stiffness matrix dependent on the number of the vector index I, multiplied consequently by the matrix of cosines and sines, auxiliary matrix of the transforming of from the transforming of vectors from global coordinate system to local coordinate system, matrix of cosine and sine, 6 by 6, 6-dimension matrix, square matrix, and multiplied by the displacement we got in the global coordinate system of the ends of, instead of the displacement of nodes, but we got the vectors of the displacement of the ends. We, for each finite element, have 6 ends, 2 ends, and 6 displacements, 3 displacements, 2 translational, 1 angular at the beginning of each finite element, and 3 displacement at the end of finite element, as well translational and 1, and bending, the rotational displacement 1. So this consequently means use that how do the what is the force in the finite elements due to the displacements of the end of each finite element. These 3 factors produced together in the considered sequence. And this is how do the external distributed force acts on the forces as a summand, as the forces acting in each finite element. So under the displacement, the force, the effort could be force, longitudinal force, or transverse force. So it can be the bending moment acting at the beginning or at the end of the elements. How do this depends by the formula on the displacement of the ends, transformed this matrix T and product by displacement delta transformed from the global to local coordinate system, and how does the forces and 2 efforts and one, the bending moment in each node of the in each of 2 ends of the rod finite element depends on the distributed load when we just transmit the distributed load to the concentrated equivalent load at the end of finite element. And this formula in the Mathcad gave us the results. The results of the forces, this is decision of the initial issue of the determination of forces in the finite elements of the statically indefinable mechanical system, the frame, rod mechanical system frame. So this is the longitudinal force, the same longitudinal force applied at the beginning and applied at the end of the first finite element, the vertical stand between the node 1, the embedding of the stand in considered mechanical system, and this one, this embedding, the longitudinal force in the local coordinate system associated with the finite element. The second one is at the end of the system, this transverse force, and this is the bending moment at the embedding of the first finite element. This is the bending moment in the rigid corner of the connection of the first finite element to the second finite element. So the efforts, the forces and the moments acting on the second finite element, the horizontal beam between the node 2 rigid corner and the hinge 3 of the considered 5 times statically unifiable frame. This is a longitudinal force 56.807 minus 56. This is longitudinal forces in the system local system associated with this second finite element. And this is the transverse force. And this is transverse force as well, the bending moment at the beginning and at the end of the finite element. So we can consider that the bending moment at the beginning of the second finite element is equivalent to the bending moment at the end of the first finite element, because they rigidly connected in the corner number 2, the second node of the mechanical system. Third inclined segment of the mechanical system, statically definable frame. The longitudinal force increases due to at the end of the force is much there's another longitudinal force, because this depends longitudinal force distribution on the distribution of the distributed load on the third inclined finite element. We have two components of the distributed force application. So this is a transverse force as well. The bending moment in the node 3 is the beginning of this first of 3 components. Correspond to the beginning of the third finite element. The longitudinal force, the transverse force, and the bending moment at the beginning of finite element. But the beginning is the hinge connection to the other finite element. So we have 0 moment, etc. And the finite element number 4, the vertical stand between the node 3 hinge and the fixed hinge in the support. So we have just only the longitudinal force. That is the determination of the forces acting on the element of the mechanical system, statically definable frame, by the finite element method in the computer algebra system Mathcad. Questions and comments. 4.15.1 matrix transformation from local coordinate system to the global system, rotating the axis, and from the global coordinate system into the local system, canceling the rotation of the axis by multiplying the matrix of direction cosines and sines by the coordinate vector of the section of the rod finite element for the initial and final sections of the element. Yes, we use the auxiliary matrix of the cosines and sines of the angle of the inclination. This looks like the quasi-diagonal matrix of the dimension 6 by 6 for the flat state, I mean on the plane, and the 2 diagonal segments of 3 by 3 filled by the sine, cosine, and just one is an element of number 3 and number 6 in the cosine and sine matrix. And if we multiply this matrix on the vectors in the global coordinate system, we will have the magnitudes of the components of vector in the local coordinate system. This use of matrix of the transformation, the geometric matrix, vector geometric matrix of the transformation. 4.15.2 determining the vector of n displacement in the local coordinate systems by multiplying the auxiliary matrix, the cosines and sines, by the vector of the displacements in the global coordinate. Yeah, this is almost the same in the when determining the vector in the local coordinate system. To determine the global coordinate system exactly, we have to do the operation with the inverse matrix to the matrix of the sine and cosine. We have to determine the inverse matrix to have the transformation from the local coordinate system to the global coordinate system. The inverse matrix is no big deal. In the Mathcad, we can do that as just only the assigning for the cosine and sine matrix the power, like cosine and sine matrix, to the -1 power, will have the inverse matrix of the cosine and sine. And applying the inverse matrix, we will transform the vector from the local coordinate system to the global coordinate system. The transformation from global to local is by the multiplication of the cosine and sine matrix onto the vector in the global system. We will have the vector in the local system. Otherwise, we have to multiply the inverse cosine and sine matrix on the vector in the local coordinate system. inverse cosine and sine matrix to the vector of the local coordinate system, and we will have the vector in the global coordinate system. This is just the simple show in the vector geometry. 4.15.3 end forces in the rod finite elements of the mechanical system where the internal forces corresponding to the longitudinal force transverse force and bending moment equal to the sum of the forces on the rod finite element from other finite and the external load action on the finite element. Yes, so the forces in the finite elements depends on two components of the action, external action onto the finite element. The first is the action of the other finite element due to the displacements of the beginning and the end of the considered finite element. And this displacement cause is considered as well the stiffness of the considered stiffened element and local coordinate system stiffness matrix. This displacement cause of the ends of the finite element, the one component of the forces arising in the finite element. And the second is the distributed load within finite element just reduced to the ends of finite element as well is the factor of the internal forces in the finite element. Uh, 4.15.4, the number of end force components for a finite element on a plane and in space associated both with the vector geometry of mechanical system and with data arrays whose size corresponds to the number of finite elements. So the number of the end force components for a finite element in a plane is usually 6, the number of the components, because we have two ends of the finite element, and we have on the plane two for each end 3 components of the efforts, 2 forces and 1 moment applied to each end of the finite element. So together we have 6 on the plane. 4.15.5 determination of end displacement vectors in the finite element in Mathcad and local coordinate system. Here finding the components of these vectors, which in turn are multi-component vectors according to the number of finite elements. The displacement vector in the Mathcad and local coordinate system is determination the sequence. First, we have to determine the displacement of the finite elements. This means that the end of the finite elements displacements of the ends of each of 2 ends of rod finite element by in the global coordinate system if we have the displacement of the nodes. So we first have to define the correspondence between the displacements of nodes of the discrete model in the global coordinate system, and by this correspondence we can find the displacements of the ends of finite element and global coordinate system in displacement parallel to axis and ordinate axis of the integral mechanical system, the global coordinate system. And after that we can use the auxiliary matrix of transformation, the cosine and sine matrix, to transform the displacement of ends of the finite element in the global coordinate system to the displacement of the ends in the local coordinate system. In the local coordinate system we have the longitudinal displacement and the transverse displacement, as well as the angular displacement, which correspond to longitudinal force, transverse force, and the bending force and the bending moment of the ends of at 2 ends of rod finite element on the plane, at each of 2 ends of rod finite element on the plane. 4.15.6 finding auxiliary vectors in the Mathcad, taking into account existing similarities in mathematical knowledge when determining the vector of end forces from the influence of a load applied within the finite element for other elements in the flat frame. The generalization of end force vectors in local coordinate system of rod finite elements into the common array in the Mathcad. To find the vectors in the Mathcad, first usually we have to define these vectors in the available set of the beforehand decisions for single span statically definable finite elements, rod finite elements available. When first we classify the finite elements into the 4 types. So first type is embedded by both ends, the second type embedded by the beginning, hingely connected by the end. Third type hingely connected at the beginning and embedded at the end, and force type hingely connected at both ends. And for each of the finite element type, we can find the before decision in the textbook, in the directories, or in the available information from the internet. This how to simplify the decision. Thus, we distribute static definability of the mechanical system considered by the finite element method to the beforehand decision of static indefinability of separate finite elements of the mechanical system, combining these elements together by the discrete model. So, but the analogies we use, we have to find originally the analogic finite elements from the set with the beforehand decisions of dependence of the end forces and moments, dependence on the external distributed load distributed within the finite element. So we have to substitute this load distributed by the finite element. We have to substitute this by the forces and moments acting to the ends of the finite element, because this is concept of the finite element method that we have to consider the load concentrated to the nodes. Nodes is the ends of finite elements. The generalization will enforce vector local coordinate system of road finite element to the common array in the Mathcad. To do that, usually we can use consequently 3 times. If we have 4 types of the finite elements, we can use consequently 3 times the operation if. If is the parameters of the if operation in the brackets. The first is the condition, is it true or false, and next after the comma we have the definition if the condition is true, and if not true, the next after the second comma we have the decision, the definition, if not if. So consequently uses this independence on the number of finite elements and on the type finite element, because beforehand we can assign the type finite element dependence on number. In that using this, we can consequently find the rule. We can define the rule of the combining of the separate force vectors into unit 1 array. In that the computer algebra system Mathcad will consider this separate force vectors as one array, independent on the number of the finite element and the corresponding type of finite element. 4.15.h, finding the end forces in the local coordinate systems in the Mathcad of the finite elements of the given statically definable flat frame. Yes, I did tell about it a little bit. So we have to find the beforehand decision. This is a benefit and the feature of the use of the finite element method, almost the same as the use of the sometimes the use of the displacements method in the decision of the statically definable mechanical system. Displacements method, perhaps we remember we told about that in the chapter 3 of the book. The use of canonical equations of displacement method as a deformations compatibility rule for the statically definable mechanical systems. And then we, as well as indefinite element method, we used the beforehand decisions for the single span statically definable frame, when we can assign sometimes unit displacements for the statically definable single span frame finite element. We can have in the unit displacement to define what is the stiffness, the force equivalent to unit displacement, for example, or the displacement equivalent to the unit force, something like that. Or we can determine what is the support reactions when we have the distributed load within the single span statically definable finite element. We can do that indefinite exercise, but this is difficult and not logical, because we can find this ready for the single span standard loaded statically definable rod finite element. We can find and use as a combined this in the mechanical system by the methods of the vector geometry and algebra, which is within the finite element method. And let me come to Mathcad page. Yes, this is decision in the Mathcad. So having decided about the displacements, I'm not talking about the scale of the displacement, the dimension, etc. Anyway, it depends as well on the specified characteristics of the elasticity and stiffness. This is displacement got of the nodes of the discrete model, and having this vector of displacement of nodes, 5 displacements of node of the model, we can define the correspondence between the displacement of the ends of the first, second, third, of the first end at the beginning at delta 1, delta 2, delta 3 is the angle of the rotation, the bending. This delta 1, delta 2 is the translational displacements in the global coordinate system of the beginning. This all three of the beginning of first, second, third, and fourth finite element in the considered issue. And this 3 is the translational displacement delta 4 and delta 5, and the angular displacement delta 6 of the end of the rod finite element of the first, second, third, and fourth finite element. So, and we define the displacement in the global coordinate system of the ends of all finite elements in the considered issue. We combine this total in the one vector function. Vector function is the dependence on parameter variable. Parameter is the number of definite element. So we have this vector function. After that, we had the before had decisions of the what is the end reactions for the standard loaded, statically definable, standard loaded by the distributed load, statically definable single span finite elements, rod finite elements, independence on the type of finite element, on the embedding of the type. I will repeat again what four types of the embedding we have of the rod finite element, but the formulas is a little bit complex, so we can allocate the common parts of the formulas of the end reactions for the vectors of end reactions is 1, 2, 3, 4, 5, 6. Each vector of 6 components, so 3 reactions, 2 forces in the moment, 2 forces in the moment in the single span finite element of the first type. And we can define what is the components if we set these vectors. These vectors A, B, C, this is functions, but this sign available in the Mathcad when we can access the matrix panel of the Mathcad, and we can find in the matrix panel the first option like the vectorization. Vectorization we did, and in the next Mathcad considers the symbol A as the vector. So we use as a vector as here a vector dependent on the I number of definite element, etc. This is a check of the elements of the finite element, all zeros, because the first finite element do not experience the distributed load. And where is the distributed load? Distributed load in the common parts of the formulas are located here. The horizontal component of the distributed load, vertical component distributed load, the vertical, horizontal, the horizontal, vertical. So in the allocated parts, we have the influence on the distributed load onto the end reactions of the finite element of other types. This is, and after that we have the same like here operation of the combining of the common array of the separate. Here we had for the separate, for the other types of finite elements, separate stiffness matrices we combined in the unit 1 array, consider it as one function matrix dependent on the number of definite element by the Mathcad computer algebra system. And here the same, we combine the unit one array by consequent use of 3 times of the if operation with 3 parameters inside of the if of the previous one, 4 decisions for any types of the any first, second, third, and the fourth numbers of the rod finite element and the considered mechanical system. At the same time, they are the predefined above 4 types of the finite elements. We have definition of the types of finite elements as a vector dependent on I. So we have T. T is a vector, transposed description is vector dependent on the index I, yes. And here we have the here we have the dependence on number and the common array of the end forces dependence on the type of finite element, and we exclude the number of the type because the factor I is the number of finite element correspond to the type of the finite element and to the end forces vector appropriate. And using this formula, this is two summands. This is the influence of the end forces, and the forces under the action of the distributed load within each of the finite elements influence on the forces applied to the end of the finite element instead of the distributed load. This is a substitute of distributed load because the concept of the finite element method is the use of the external load only applied to the nodes. So this is the impact of the distributed load applied to the node, substitute by the forces applied to the nodes, and this is the summand of the forces acting at the ends of the finite element as the consequent product of the stiffness matrix of the dependence of the number of finite element, which one stiffness matrix we have to use, and what is the data for the stiffness matrix in the local coordinate system. Next product by the auxiliary matrix of the transforming from global to local coordinate system. This transforming from local to global, and this is the product of these two summands, the onto the displacement in global coordinate system. These together two factors means the displacement of the ends in the local coordinate system. This longitudinal displacement, transverse displacement, and angular displacement. This result of the product this matrix onto the array of vectors. And as in the global coordinate system, this together we consider as a delta stroke displacement in the local coordinate system. But in the local coordinate system, the displacements mean the horizontal displacement along the global axis x associated with the integral mechanical system, and the displacement along the ordinate axis associated with the ordinata of the global coordinate system vertical direction, and the angular displacement. And in the local coordinate system, we consider this displacement as a longitudinal displacement of the end along the axis associated with the axis of the finite element. The longitudinal force that gives us the transverse direction in the direction of the transverse force associated with the finite element, and the angular displacement the same as in the global coordinate system. So after the action together, we have the decision what is for 4 finite elements we had assigned in the statically definable frame. What is the magnitudes of 1, 2, 3 efforts applied to the beginning of the first finite element. First finite element is vertical stand between the node 1 and node 2 rigid corner between the first and the second finite elements. And this longitudinal force applied at the beginning and applied at the end with the same magnitude, but the other side. This is transverse force applied at the beginning, at the end of the finite element, the same magnitude, other side. And this is the bending moment. In the node 1 is the embedding of the first finite element, and the bending moment at the end of the first finite element, the connection to second finite element in the node 2. The same bending moment we have here at the beginning of the second finite element, because the rigid corner connection transmits the bending moment to the another part of the mechanical system, to the second finite element as well. Now we have longitudinal force in the second finite element 56 at the beginning, of 56 at the end with another sign, and transverse force as well we have. For third finite element, the inclined rod hinged in the node 3 to other finite elements and embedded at the node 4. So this is a longitudinal force at the beginning and at the end of the finite element. So the difference is because this depends on the action of the distributed load within the third finite element. Yes, third finite element is under the action of two components of the distributed load. And the transverse force and zero moment, because the third finite element connected at the beginning. This first three components at the beginning, the next three components at the end. Zero moment at the beginning because the hinge in the node 3 do not transmit the bending moment, and the embedding at the end of the third finite element is of the moment. This is the bending moment, and the fourth finite element, the vertical stand between the nodes 3 and node 5 of the considered mechanical system. This stand, the hinge connected by both ends, at both ends, experiences only the longitudinal force at the beginning and at the end, the same magnitudes, but other signs of the longitudinal force applied to the ends of the fourth finite element of the considered mechanical system. Thank you.